I was grabbing a coffee with an old colleague last week. The kind of guy who tracks every Silicon Valley rumor like it's his job. He had his phone out, and he was scrolling through a teardown of the latest Huawei Mate 60 Pro, and he was practically smirking. It's a parlor trick, he told me, tapping the screen. Sure, it's a 7-nanometer chip. Sure, it works. But they're just using old tools they bought from the Dutch or the Americans. It's like finding a Picasso and claiming you're a master painter because you managed to buy the brush.
Right, the old fast follower narrative.
Exactly. He was leading right into that comfortable story we've all heard. China, as a world-class copycat, can drive the car, could never build the engine. There was this real sense of security in his voice. Like, as long as the West held the keys to the factory that makes the factories, the global hierarchy was safe.
It wasn't about the chip, it was about the permission to make it.
That's it, exactly. But then I asked him just one question. I said, what happens when they stop trying to buy our brushes and start growing their own bristles? I showed him a technical brief on ASML, the Dutch giant that makes the world's most advanced lithography machines. I described the process, how they use these high-powered lasers to blast droplets of molten tin 50,000 times a second to create a plasma that emits extreme ultraviolet light. I mean, it's a machine so complex, it's been described as trying to hit a postage stamp on the moon with a rifle.
Which is not an exaggeration.
Not at all. And I pointed out that while we were busy, mocking the copycat, a staggering $47.5 billion was just injected into a new Chinese state fund specifically to build those exact machines from the ground up.
And his expression.
It shifted. Instantly, the smirk didn't just fade. It turned into this focused, really uneasy silence. He got it. He realized the conversation had moved on. We weren't arguing about lap times or who has the fastest car anymore. We were talking about the guy in the grease-stained garage who is tired of being the driver and has decided to invent a whole new kind of engine. And that shift from using the tool to owning the tool, that's the ghost in the machine that I don't think anyone is prepared for.
And that right there is the perfect summary of why this deep dive is so critical today. For years, the whole tech discussion was about the product, the sleek phone, the fast GPU. But under the surface, the real story, the real power, has always been about the structural bottleneck of global tech. And that bottleneck has a name: Extreme Ultraviolet Lithography, EUV.
So if I'm getting our mission today right, we are. We're skipping the gadgets. We're going straight to the fundamental engineering reality of it all, looking at that pivot you mentioned, from driving the car to inventing a new kind of engine.
That's exactly it. Our mission here is to explore the technical reality behind China's intense state-led push for technological sovereignty. We're going to map out the huge investment, like that $47.5 billion big fund you mentioned, and then we'll get into the weeds. We'll look at the specific engineering breakthroughs, both the ones in mass production and the prototypes that's just fundamentally speeding up the whole timetable for chip independence.
Moving the conversation from the boardroom to the atomic level. Okay, let's start there then. At that atomic level, for anyone coming into this cold, they might not really get that the entire modern digital world basically rests on one company, ASML in the Netherlands, building one very specific machine. So what is EUV lithography and why is it such a pinnacle of engineering?
Okay, so EUV lithography it's the foundational technology for manufacturing the most advanced chips. We're talking nodes below 7 nanometers. These are essential for modern AI accelerators, 5G gear, high-performance processors, all the top-tier stuff. What makes it revolutionary is the light it uses. It operates at a wavelength of just 13.5 nanometers.
13.5 nanometers. That sounds incredibly short. To give some perspective, how does that compare to, say, the light we can see or even the last generation of this tech?
It's a massive leap. Visible light is in the hundreds of nanometers. The older standard, which is still a workhorse for most chips, is called deep ultraviolet, or DUV, and DUV operates at 193 nanometers. So going from 193 down to 13.5 is it's like switching from carving a statue with a chisel to sculpting it with a single hyper-focused laser beam.
And that move to such a short wavelength, it completely changes the game for chip manufacturing.
It makes everything more efficient. With EUV, you get what's called single patterning precision at those super small nodes, like sub 5 nanometer. You lay down your circuit pattern in one go, and it's done. It simplifies the process, and crucially, it boosts your yield.
So if EUV is the simple, elegant path, what's the alternative? What do you have to do if you can't get your hands on an ASML machine?
The alternative is It's brutal complexity.
Yeah.
If you want to make, say, a 5-nanometer chip using the older 193-nanometer DUV light, which is what China is forced to do because of export controls, the wavelength of that light is just too big to draw the lines properly in one pass. So you have to resort to these incredibly costly, complex, and inefficient techniques called multi-patterning.
Help me picture that. It sounds exhausting just from the name.
Imagine you need to draw a very, very thin line, but your pen is too thick. So instead of drawing it once, you draw 4 slightly different, thicker lines next to each other, and then use chemicals to etch away everything in between, leaving just the thin line you wanted. That's essentially what self-aligned quadruple patterning, or SAQP, is. 4 separate steps of exposure and etching.
And the real-world consequence of all that extra work?
It kills your speed and your efficiency. You're running the same silicon wafer through the machine 4 times just for one layer of the chip. And the critical part is, with each extra step, you basically cut your production yield in half because you're introducing more and more chances for a tiny defect to ruin the whole thing. It's expensive, it's slow, and it's complicated.
Which is why EUV is the gold standard. It just gets it done in one clean shot.
Exactly. It holds the keys to high-volume, cost-effective advanced chip making.
Okay, so we know EUV is king. But why is ASML the only company that can build them? What's the barrier here that's been so hard to overcome for decades?
This is where you really see why it's called the most complicated machine humanity has ever built. A single machine costs about $200 million. And that price tag reflects this insane combination of plasma physics, ultra-precision optics, and high-energy lasers, all working in perfect harmony.
Let's break that down. Tell me about the light source. The part you said was like trying to hit a postage stamp on the moon with a rifle.
That analogy is dead on. To create that 13.5 millimeter light, you can't just use a fancy light bulb. ASML's method involves firing 2 separate QO-Euros lasers at a tiny droplet of molten tin. And these droplets are about 30 microns in diameter, maybe a third the width of a human hair.
And how fast are they doing this?
50,000 times per second. The first laser zaps the droplet to vaporize it into a little cloud. The second, much stronger laser then blasts that cloud, heating the tin to such an extreme temperature that it becomes plasma. As that plasma cools for a split second, it emits the 13.5 nanometer light you need, the precision to hit a microscopic, moving target with 2 different lasers 50,000 times a second. That's the rifle shot on the moon.
So that's the physics problem. Then you have the optics. This light is so extreme, it can't go through glass lenses, right? So it has to be mirrors. And I'm guessing not the kind you have in your bathroom.
Not even close. These are ultra-precision mirrors made exclusively by Carl Zeiss in Germany. The 13.5 millimeter light is so energetic it gets absorbed by almost everything, even air. So the entire machine has to operate in a near-perfect vacuum. The light then bounces off a whole system of these special mirrors, and they have to be, well, perfect.
I remember reading about the surface of those mirrors. The smoothness is legendary.
When we say atomic level accuracy, we mean it. If you scaled up one of these mirrors to be the size of Germany, the biggest bump on its entire surface would be less than 1/10 of a millimeter high. Polishing something that big, that flat. That's why it took Zeiss and ASML decades to perfect.
And the final piece of the puzzle is the supply chain itself, because all these critical parts are made in different places by different specialists.
Exactly. The lasers come from Cymer, a U.S. subsidiary of ASML. The optics are from Germany. The integration, the secret sauce that puts it all together, is Dutch. This creates a huge barrier to entry. If you're blocked from buying the machine, which is what U.S. export controls did starting in 2019, you don't just need one breakthrough. You have to replicate 5 separate, globally monopolized technologies all at once and then make them work together flawlessly.
It really is an engineering fortress. And yet, the reality on the ground is that the very restrictions meant to stop progress seem to have just kicked off this accelerated state-led mission for resilience.
That necessity is what drove China's dual strategy for getting to 5 millimeters and beyond. It's a race fought on 2 fronts. You've got Path A, which is about immediate results, mastering the constraints of the DUV tech they already have and pushing it to its absolute limit. And then there's Path B, the long game, building a domestic EUV tool from the ground up.
Let's take Path A first. Mastering the constraint. The world was genuinely shocked when the Huawei Mate 80 series came out with what was basically a 5-nanometer class chip inside. It proved you could get there without EUV.
It was a massive technical statement. SMIC, the manufacturer, achieved volume production on what they call their N+3 node. And the key phrase there is volume production. This isn't some lab experiment. It's a chip in a phone you can go out and buy.
And to do that, They had to use that incredibly complex technique we just talked about, self-aligned quadruple patterning, SAQP.
That's right. To get down to that 5-millimeter feature size with 193-millimeter DUV light, you need those 4 separate exposure and etching steps. And think about the cost. Not only does it take 4 times as long, but you need incredible precision with all the chemical spacers and films. If one tiny defect happens on the first layer, it just gets worse with the next 3.
The cost must be, just staggering compared to the clean, one-shot EUV process.
It's dramatically more expensive, which is why the rest of the world moved to EUV as fast as they could. But, and this is the crucial point, for a state-led effort where national security and technological sovereignty are the goals, efficiency is secondary to capability. The fact that they pulled it off shows a deep, deep level of engineering capacity.
And the evidence suggests that capacity is improving fast. We're seeing reports of rapid yield improvements on their advanced AI chips, for instance.
That's the most important metric to watch. Huawei reportedly got production yields for their advanced AI chips up to nearly 40%. Now, that's still below the leaders who are using EUV, but it's a huge jump. The year before, those yields were only around 20%.
So they basically double the yield in a year.
In a single year while under sanctions using these incredibly complex workarounds, that shows an exponentially steep learning curve inside SIMIC and Huawei.
And this wasn't just about SIMIC getting better at one technique. It required building out an entire domestic production line, right, to get away from foreign tech.
Absolutely. That 5-millimeter class line is a testament to that goal of industrial independence. Reports say it's using DUV machines from Shanghai Microelectronics, or SME, but lithography is just one step. You also need the etching tools, the measurement tools, the whole ecosystem.
So what other domestic gear is in that line?
The DUV machines are reportedly paired with other domestically made high-end equipment, things like 5-millimeter etchers from AMEC, which are critical for carving out the lines after they've been drawn, and advanced measurement tools from Nora. This is the dream of a closed-loop supply chain becoming reality. If you're cut off from foreign tools, you just learn to make every single part of the factory yourself.
Okay, so they're mastering DUV for 5-millimeter. What's the next step to keep improving performance if you don't have the best lithography? What are the architectural workarounds?
The main focus right now is on things that minimize your reliance on just making transistors smaller. The biggest one is 3D stacked chiplets.
Chiplets. The whole industry is moving that way, but for China, it must have a whole different level of urgency.
Exactly. With a chiplet design, you can take multiple smaller, less complex chips, maybe each made on an older, more reliable 7-millimeter DUV process, and you combine them into one big, powerful processor using advanced packaging. You get massive performance gains by going vertical, by stacking, rather than just by shrinking things horizontally.
So instead of making one giant, perfect 3-millimeter chip, which is super hard, you make 4 or 5 pretty good 7-millimeter chips and stack them like a high-tech Lego tower.
That's a great way to put it. You're moving the engineering challenge from the lithography machine to the packaging tool, but the ambition doesn't stop there. Reports indicate they're already developing 3-millimeter designs that use the next big architectural leap: Gate-All-Around, or GAA.
Gate-All-Around. That's a pretty big deal, moving on from the FinFET architecture we've had for a while. Could you explain that shift?
Yeah, sure. With FinFET, the transistors look like a little fence, or a fin. The gate, which controls the flow of electricity, wraps around that fin on 3 sides. With Gate-All-Around, you replace that fin with a stack of tiny nanosheets, or nanowires, and the gate literally wraps all the way around them on all 4 sides.
And why is that so critical for getting to 3-nanometer and smaller?
It gives you much better control over current leakage. As transistors get smaller, they start to leak electricity, which wastes power and creates heat. GAA clamps down on that leakage, which is what lets you keep scaling. The fact that they're already working on GAA designs shows they're planning for the future of their domestic production lines.
Now, you mentioned something even more, out there. Something that sounds like pure sci-fi. Carbon nanotube chips.
This is the high-risk, high-reward bet, the attempt to just leapfrog silicon entirely. There are reports of a carbon nanotube-based chip that's already undergoing compatibility testing on SESMIC's production line. This is a massive materials science problem.
Why is it so incredibly difficult?
Carbon nanotubes have amazing potential, way beyond silicon. But their electrical properties depend on their physical structure, specifically something called chirality.
Chirality, that's the way the carbon atoms are twisted in the tube, right?
Exactly. You need them to twist in just the right way to act like a semiconductor. Controlling that twist at an atomic level and then getting billions of perfect nanotubes to line up on a wafer, It's exponentially harder than just etching silicon. The fact that this is even being tested for production shows just how serious they are about finding any path to bypass the EUV bottleneck.
Which sets the stage for Path B, the long game, the Manhattan Project to build the EUV machine itself. What do we know about this prototype in Shenzhen?
Reports from late 2025 confirm that a functional prototype is complete and it's now in testing, and they've hit the biggest milestone. It successfully generates the 13.5-nanometer light. That proves the core physics problem has been solved at home.
Generating the light is one thing, but turning that into a machine that can actually pattern chips reliably is another. What's the current state of this prototype?
It's described as being physically huge. It apparently takes up almost an entire factory floor, which is way bigger than ASML systems, which are roughly the size of a city bus. And that size tells you a lot about its current limitations.
Why so big? Why can't they match the compact design that ASML perfected over 2 decades?
They're using scale to make up for a lack of refinement. It seems they made it bigger to handle much higher power demands and to compensate for less sophisticated subsystems, especially with the optics and managing heat. You need bigger motors, bigger vacuum pumps, more space for cooling, all because you haven't yet achieved the super high efficiency that ASML gets from its integrated global supply chain.
What about the timeline? This is where the speed really highlights the pressure they're under. How does it compare to ASML's own development?
The contrast is pretty dramatic. ASML started its EUV research around 2001 and didn't really have a commercially ready machine until 2019. That's an 18-year path, working with hundreds of partners worldwide. China is trying to compress that 18-year, multi-billion-dollar R&D marathon into maybe 8 to 10 years.
8 to 10 years. That is a staggering compression of the learning curve. What are the internal targets looking like?
The official target is very ambitious, producing working chips with this thing by 2028. Now, insiders think 2030 is more realistic for it to be truly ready for industry. But even 2030 is way faster than most Western analysts predicted. It just shows the immense resources and singular focus behind this national project.
Now, Path B isn't just about copying ASML's method. I understand there's another parallel project using a totally different approach. Localized dynamic patterning, or LDP.
That's right. LDP is basically Huawei and SAQP's bet on finding a completely different way to generate the 13.5-millimeter light, one that doesn't require them to replicate ASML's incredibly complex laser system.
So how does LDP make the light if it's not using those big COP08 lasers?
Instead of blasting tin droplets with lasers, LDP uses a high-voltage discharge. It essentially vaporizes tin between 2 electrodes and then converts that vapor into plasma with a very, very fast and powerful electrical spark. So it's using a spark instead of a laser blast to get the job done.
That sounds like it could radically simplify the whole machine.
That's the main potential advantage. If you can get rid of the complex lasers and all their alignment optics, you could potentially simplify the architecture, shrink the machine's footprint, maybe avoid that factory-sized prototype problem, and even make it more energy efficient.
And what's the timeline for this LDP alternative?
The timeline is extremely aggressive, which tells you how seriously they're taking it. They're reportedly aiming for trial production in the 3rd quarter of 2025, with mass production targeted for 2026. Now, and it's a huge if, LDP proves to be viable and scalable, it could be an even faster route to sovereignty than just replicating the ASML machine.
This level of synchronized, high-stakes R&D across multiple different physics pathways, it just doesn't happen organically. Which brings us to the strategy and the people behind it all, the architects of this sovereignty push.
And it all starts with the money. You have to look at the massive strategic financial commitment from the China National Integrated Circuit Industry Investment Fund, what everyone calls the Big Fund 3. This new phase isn't just about cutting big checks, it's a fundamental shift in strategy.
We're talking about $47.5 billion.
Yeah.
How is that money being targeted differently this time around?
The earlier phases were more about just boosting overall production volume. Big Fund 3 is laser-focused on the strategic bottlenecks that the export controls exposed. So the key targets are high-precision lithography systems, all the foundational manufacturing tools for the fabs, and this is critical electronic design automation, or ED software.
EDA software. That's the blueprinting software for designing chips, which has been totally dominated by U.S. firms.
Yeah.
So going after that, alongside the lithography machines, confirms this is a full-stack effort.
Precisely. And the investment strategy has changed, too. They're holding investments for longer and trying to force industry consolidation to get these really hard breakthroughs done. The strategic implementation of Big Fund Phase 3 is what's really catalyzing this paradigm shift.
But it's not just financial, right? There's a cultural pivot happening in the engineering community, a move from just being really good at using imported machines to actually inventing the foundational tech. This is where the human stories, I think, really bring it to life. Let's start with this figure, Mr. Lin.
Mr. Lin, the master of the floor. His story is the perfect example of that shift from operation to creation.
I was reading about him. A veteran engineer, spent 20 years in a high-tech park in Suzhou. His whole career, he was the guy who could squeeze that extra 1% of efficiency out of the imported litho machines. He knew them inside and out, better than the manuals. But he was always constrained. If a core part failed, the keys, the software, it all belonged to a company an ocean away.
He was a world-class operator who was always operating with someone else's permission. He could make the car go faster than anyone, but he never had the blueprints to the engine.
So when Big Fun Third started pouring money into domestic manufacturing tools, Mr. Lin didn't retire. He joined a domestic startup. And now, instead of just optimizing a machine, he's reportedly spending his nights staring at blueprints for high-precision lenses, trying to solve the very bottlenecks he used to have to work around.
That's the dignity of the craftsman. It's the move from being a user to being a creator. For people like him, this is about true industrial sovereignty. He realized the ultimate problem wasn't the physics, it was access to the tools. The Big Fun gave him the chance to stop being the driver and start being the inventor.
And that cultural shift connects to that second paradigm change.
Yeah.
The whole national identity moving from just being a high-volume manufacturer to being a primary innovator.
And that transition from a high-volume manufacturer to a primary innovator of the equipment itself, that's a huge milestone. It's about achieving that long-term technological sovereignty. And this is perfectly captured by the story of researcher Zhao in Hefei.
Right. Imagine being a researcher Zhao, working under this immense national pressure to innovate. She grew up when made in China meant quantity. Her whole career is now defined by this shift to primary innovator. I read this post detailing how her team was trying to redesign one specific critical component for a lithography machine. They failed 400 times.
400 failures. That's not just bad luck. That's the brutal reality of engineering when you're in uncharted territory. Every one of those failures was an expensive lesson, a reminder of the massive IP gap they were trying to close.
But when they finally had their breakthrough, the story said the celebration wasn't some big press conference. It was just a quiet, exhausted dinner where they all knew they had finally stopped copying the homework and had started writing the textbook.
And that says everything about the shift in aspiration. It's not enough to be the factory of the world anymore. The goal is to be the laboratory of the world. That human drive, that desire to be the architect, not just the builder, is an incredibly powerful engine. And now it has all the state funding it needs.
Which brings us to the sheer scientific commitment required here, to taming the impossible physics of EUV.
The rapid evolution of their domestic ecosystem really shows a profound commitment to mastering these incredibly complex physics and engineering challenges. It's about building the whole infrastructure from the ground up.
This is where we get into the pure science behind it, and that anecdote about Dr. Chen.
Dr. Chen, an optical engineer working on the mirror system, he reportedly described his work not as engineering, but as taming light. To make these next-gen chips, you have to manipulate that 13.5-millimeter light on a scale so precise that, again, it's like hitting that golf ball on the moon.
And what was the specific challenge he pointed to?
He emphasized that you just can't rush patience. You can't steal the years of painstaking calibration it takes to polish a mirror to atomic smoothness. It might take 5 years of trial and error just to perfect the process for making one component. It's a localized, agonizing human struggle against the limits of what was thought possible.
So that $47.5 billion isn't just buying machines. It's buying the time, the years of focused human commitment needed to solve problems that the global industry took 2 decades and a massive international effort to figure out.
Exactly. The physics doesn't care about geopolitics. A breakthrough needs brilliant people, time, and, well, almost unlimited resources focused on one single goal. And that focus is the ultimate engine of this whole pivot.
Okay, let's shift gears a bit. While all this hardware catch-up is happening, how are they bridging the compute gap right now? We've talked about the long game, but how are they staying competitive in the short term, especially in a field like AI?
The strategy has been an intense focus on software innovation as a path to parity. They are, in effect, bridging the compute gap with really aggressive software optimization to get the absolute most out of the domestic hardware they have today.
Can you give us a concrete example of that? What does that optimization look like in practice?
It looks like manipulating data formats. So, for example, companies like DeepSeek have been championing the FP8 data format. In AI model training, precision is usually measured in 16-bit or 32-bit floating point numbers. FP8 means using just 8-bit precision.
Which sounds like a step down in quality. Why would you want lower precision?
Because for a lot of AI training, you don't actually need that extreme mathematical precision. By using a smaller, highly optimized 8-bit format, the hardware can process way more data way faster. It maximizes the performance you can squeeze out of technically older hardware.
So by standardizing the software around formats like FP8, a domestic processor, even one made with that complex DUV process, can start to punch above its weight class.
It's an end run around the physical hardware limits. This software-first approach means their domestic processors, like the Huawei Ascend 910C, are achieving training performance that's comparable to restricted Western hardware like the NVIDIA H100, even though the silicon itself is technically a generation or two behind.
So the compute gap isn't a fixed distance anymore. It's a systems engineering problem where software can buy you time for the hardware to catch up.
That's the strategic reality. By becoming masters of efficiency, they're staying competitive in the critical field of AI while the years-long hardware race continues.
This whole race has also forced a massive restructuring of the global supply chain. It's clearly in a phase of what you could call strategic bifurcation. What does that look like on the ground?
It looks like an accelerated decoupling, and it's being driven from both sides. On one side, you have the China Plus One strategy really hitting its stride. You see multinational corporations moving their assembly and testing operations out of China and into new hubs.
And where's all that capacity going?
Vietnam and Malaysia are the big winners. Malaysia, in particular, is now one of the world's largest semiconductor exporters, especially for packaging and testing. The supply chain is becoming geographically diversified, creating these parallel, redundant systems.
But China isn't just watching this happen. They're using their own leverage in response.
Absolutely. We're seeing them use their control over raw materials as a tool. They've intensified export controls on critical materials like gallium and germanium, and on rare earth elements. These are all essential for making advanced electronics. So it's a tit-for-tat escalation where each side uses its unique leverage to create friction for the other.
Now, despite all these breakthroughs, there's a big storm cloud on the horizon for Chinese fabs. The ones that still rely on all the Western equipment they bought before the sanctions. I'm talking about the maintenance crisis.
This is maybe the most immediate long-term threat they face. Most of the big Chinese fabs are built around Western-made DUV equipment from ASML, Lam Research, Tokyo Electron. And there's intense geopolitical pressure on these companies to stop servicing those machines, to stop supplying spare parts.
So if the maintenance stops, what happens to those advanced DUV lines that are making the 5-nanometer class chips right now?
Without routine service and replacement parts, those lines will eventually degrade. Their performance will drop, and eventually they'll grind to a halt. The clock is ticking on the operational lifespan of all that imported equipment.
And how is the domestic industry planning for that?
Two main ways. First, you'll see a surge in a gray market for parts and services, probably routed through third countries. But the more fundamental response is a massive state-backed push for domestic replacement parts for all this semiconductor manufacturing equipment, or SME.
So reverse engineering the consumables, the hardware parts of the DUV machines, to keep them running forever, no matter what happens with foreign service contracts.
That is the ultimate goal. I mean, if you're already investing $47.5 billion to build an entire EUV machine from scratch, manufacturing a spare part for an older DUV machine is an achievable goal. This whole maintenance crisis is just another driver accelerating the development of a fully domestic equipment industry.
It brings us right back to where we started. It's not about buying the brush anymore. It's about growing the bristles, making the handle, the ferrule, and mixing the paint yourself.
And that's the core takeaway here. The compute gap isn't some fixed number anymore. It's a moving target, influenced by physics, by software, and by sheer human commitment. The old assumption that export controls would just stop advanced manufacturing in China, well, that's been proven wrong by the 5-nanometer breakthrough and the existence of that EUV prototype.
The incredible capacity for state-led innovation, fueled by all this money and the focused efforts of engineers like Mr. Lin and Dr. Chen, it suggests that the strategic advantage of the export controls, it might start to diminish over time.
The whole conversation has permanently shifted. We've moved from arguing about who has the fastest chip to who has the keys to the factory floor.
And who's building the next factory down the street?
Exactly. The technological pivot isn't a theory anymore. It's an engineering reality, and it's moving fast. The events of the last year or so really mark a definitive end to that era of globalized semiconductor cooperation. We're in a new, high-stakes, fragmented reality now where technological sovereignty, backed by massive investment and human dedication, is the ultimate currency of power.